presentation is about quantum dot synthesis and its characterization. And we here prepare cadmium chloride quantum dot along with some different types of quantum dots. Not only cadmium chloride, but as cadmium chloride is required most of the cases, so we use cadmium chloride here. And along with like zinc, selenium, and some mercury, and some other tellurium, and different type of heavy metal we use for quantum dots. But we found that cadmium chloride has the biggest interest application in different purposes for biological sciences. So that's why we use cadmium chloride frequently. That's why we prepare here. And we previously used different methods of cadmium chloride, but after all we found some methods are really standardized and it can be used in different purposes. So we, like say for example, here we prepare cadmium chloride and we call it we number it like this cadmium chloride 15. And say for example we use some different chemicals for surface modifications of cadmium chloride. But it depends on the experiment and how we design the experiment that is for. So use of cadmium chloride here, we use marker to succinic acid, and but this use of cadmium chloride I already mentioned it. And the preparation is like that, marker to succinic acid we use and on the cadmium acetate, and we mix with water, and then ammonia solution was used to maintain the pH, and after we use sodium borohydrate, and we mix for like 3 hours or 2 hours until the hydrogen bubbling stops, and after that we make the volume up to 101. We cook in, better to say is heating in microwave for different temperatures. So this is the picture that we use here, and the solution is made on the magnetic rotor, and pH is checked by pH meter that we have, and microwave we have that we can use different power and different ramping time and different temperatures, and we found that sometimes the ramping time is really important because here we use the pressure also, because the quantum dot can be prepared in open vials like as it is in most of the laboratories. But here what we get the advantage that we use a closed vials, and in this closed vial we found that the pressure is really helps us to produce the cadmium chloride in a different way, and it's very easy and very fastest way. And another thing is that why we use microwave in this way. In this case we do not need to use some organic solvents. Generally people use some organic solvents, and these organic solvents sometimes can be toxic for cells. So we use here water as solvent here. So it's we can say it's a green synthesis of quantum dot, and this is different types of quantum that we prepared with along with different temperatures, and as the temperature is growing, increasing, the size of the quantum dot is increased, and it shows different types of fluorescence. Like here, in case of 50, 60, or 70, the green is smaller, then yellow, orange, and red. And in case of red, it's really big. And after 120, if like we cook it like 130 or more, we found it's precipitated and there is no fluorescence at all in the solution. So generally we use 120, and it depends. Sometimes we found that it depends on slightly varies. Like say for example, we really want to prepare yellow, but sometimes it happens that 90 degree it shows some greenish yellow. Sometimes it depends on the environment. A little bit plus minus 5. It happens sometimes. And also another thing is that if we prepare green quantum dot and we keep it for 1 month in our laboratory, we found that it can be red after 1 month or 2 months, because what happens in the solution, they accumulate quantum dots get it together and they make it big, and when it becomes big and it really changes fluorescence. So it is always recommended to use fresh samples to have a really good quality of sample. This is the intensity of fluorescence of different colors of cadmium chloride, and This is the absorbance, and this peak shows that there is only one particle, there is no different types of particles. And what we wanted to, maybe in future we will try to prepare something, some quantum dot that can fluoresce in near infrared region, because it's needed for imaging purpose, because I know it better than me, because it's really, we have some problems, because I will show you later on that I use this quantum dot on imaging purpose, and what happens because any organic tissue, I mean any tissue of any living animal or something, they have its autofluorescence, and if we have infrared region, the quantum dot can have infrared emission, that it would be really very good for imaging purpose. So we are really trying to do this. So whatever, we try to do something more, because we thought that some coherential quantum dot can be prepared so that it can have some advantage of the materials, and it has some special type of fluorescence property, so we can use these things. So first of all, we think that cadmium radii can be covered by zinc selenium, because it will have two different metals like cadmium and zinc, and because this particle will have different metals, so we can attach it with different type of adapter or linker or whatever, aptamer or whatever. This is the purpose that we, and this is the preparation of zinc selenium. Briefly, it is like some surface modification is created by magnet or something you can see, and some protocol is not similar, but a chemical we change, and we use the microwave again here. And zinc selenium has not different color range. Only in room temperature we can have some bluish color, and 60 degree can also have a little bit sky blue color, and 80 degrees green, and 100 degrees almost no color, very faint green color. And from zinc selenium we cannot have red color. So after that, these are fluorescence spectra and observed spectra. And what we plan to do these things, and successfully we did this. And this is the cadmium chloride zinc selenium partial quantum dot. It has really big range of colors with different temperatures, and it has really good fluorescence, and we use in imaging purposes. I will show you. This is the different spectra and absorbance in different temperatures along with control. And this is some more characterizations like theta sizer. We wanted to know what is the exact size of this particle. We found it's okay for not only imaging, also we are using this particle for different purposes, different other experiments that are going on here. This is theta potential, and it shows that it's a really good theta potential, so that it can have a good affinity for other components. And this is X-ray fluorescence graph from the machine. Shows that all the metals or elements that we expected that it has in this solution. And this is TEM results, transmission electromagnetism. Maybe we need HRTM, that high resolution TEM, but we didn't have that here. And this is fluorescence intensity of this quantum dot in different depth of tissues. That this quantum dot was applied on the tissue that I will show you in the next. We use these tubes. This is some plastic-like things. It's polyester tubes, and we use this quantum dot inside the tube, and we put that tube inside the tissue, and we wanted to know what is the fluorescence intensity or the capability of getting fluorescence from if we inject in the tissue, or sometimes it happens if we inject it or it mix in the tissue, and sometimes but in that case maybe we don't know what is the exact fluorescence intensity or what is the activity of that quantum dot in the tissue. That's why you use this tube, and later on we also use the injection. We will see. Here is the fluorescence under the tissue, chicken tissues we use, and here we inject the chicken embryo with different types of quantum dots that is showing here in this insect. And say for example here we cannot find a good fluorescence by photograph, but when we apply on the tissue, chicken tissue, then we found it has not bad fluorescence. So the conclusion is that we are able to view all these quantum that we prepared, that 4 shell quantum that can be viewed under the tissue, and we can use it for imaging purposes, like we can track it, we can use it for tracking of different biomolecules that is going that can be passed through by the blood or in some vein, and we can use this under the tissue. So we successfully made this. I have to acknowledge Eva, Vidram, Abu, Adam, Professor Izek.